So good morning everyone and welcome to this lecture. In this lecture we are dealing with longitudinal waves. Longitudinal waves, and as soon as longitudinal waves come into the picture, only one thought comes into our mind. And what is that thought that comes into our mind as soon as we hear longitudinal waves? Yes? Huh? Huh? No answers? As soon as we hear longitudinal wave, what comes into our mind instantly? Nothing, sir. There is nothing in our minds. Why to have any thoughts in our mind? Useless thoughts. Yes? Does anything come into your mind when you hear the word longitudinal wave? Huh? Nothing comes in our minds. What should come in our mind is this. Yes?
Direction of disturbance and propagation.
Direction of disturbance is in the direction of propagation. Okay, what else?
Distance of sound waves.
That is the first thing that comes to our mind when we talk about longitudinal wave. The only type of wave that we are probably concerned with is the sound wave. And how is sound wave produced? It is a longitudinal wave which is produced by a vibrating source. By a vibrating source. Guitar string vibrates, produce sound. Human vocal cords are also like guitar strings. Vibrates, produces sound. The prongs of a tuning fork vibrates, produces sound. Or the diaphragm of a loudspeaker vibrates and produces sound. It's a longitudinal wave, it's a mechanical wave. Therefore, it needs a medium with properties of inertia and elasticity. We have already seen this. Yes or no? It propagates with the phenomena of compression and rarefaction. Do we know this? Yes or no? No or yes? Huh?
Yes, sir.
Ah. How is this sound wave produced? So I'll just you don't have to write everything down. You just have to understand. This is just for your understanding and not for your writing. Do we understand this? Just a repetition of what we have already done. Just giving you the context that this is a sound wave. So as you can see, this is a tuning fork, the prong of a tuning fork when it vibrates. When you vibrate it, what happens? The air molecules at some portion. See these air molecules here. These air molecules here in this pink zone. They are at atmospheric pressure. Do you see them? Yes or no? No, yes. Huh?
Yes.
Hmm. But you look at these molecules which are closer to this prong because of vibration of this prong. They have come closer. They have been compressed. This is the region of compression. Do we understand this or this has gone above our head saying bye bye? Huh?
We understood, sir.
You are understanding? Okay. Pakka na?
Yes, sir.
So, this is how you create this compression pulse or compression wave. And then if you keep on doing what? Keep on doing ding 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 ding. What do you mean by ding 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 ding? You keep on vibrating it. Eh? If you keep on vibrating it, then when you bring it away, these particles from atmospheric pressure, they become more further apart. So that is the region of rarefaction. Do we see this? Yes or no? This blue region, my dear friends. We. Do we see this? This blue region is the region of rarefaction. This pink one is the region of normal atmospheric pressure. And this green one is your pulse, the wave that you have created and it starts to move. Do we understand this?
Yes, sir.
Just gone above our heads saying bye bye.
We understood, sir.
Now, since this is a longitudinal wave and since this is a sound wave and it propagates by the phenomena of compression and rarefaction, it would be wise that to write the equation of this wave, we don't write it as displacement of the particles because particles are also moving in the same direction. When we write the displacement of particle also in the same direction, it might create some sort of a doubt. I mean, you can always do that, but it is a better thing. What better thing? To write this equation in terms of pressure, because we are basically talking about a sound wave and sound travels on earth, and at some point the pressure will be more and at some point the pressure or the density would be less. Yes or no? No, yes. Huh?
Yes, sir.
So we can write this sound wave traveling wave in terms of a pressure wave, and this is how the equation of this gentleman may look like. How the equation of this gentleman may look like in terms of the pressure wave. Can anyone tell me? Huh? Delta P is equal to delta P naught sine of omega t minus kx. Or you can write it as t minus x by v. What are these things? Huh? What are these things that I've written? Delta P is the difference in pressure between the pressure of any point and atmospheric pressure. Do we understand this?
Yes, sir.
Then what is this delta P naught? This is the maximum difference in pressure between the atmospheric pressure and the pressure at compression or the pressure at rarefaction. Do we understand this, or this has gone above our head saying bye bye? Bye bye, sir, I'm going, sir. Bye bye, sir, I'm going, sir. Bye bye, sir, I'm going, sir. Bye bye, sir, I'm going, sir.
We understood, sir.
Pakka, sir?
Yes, sir.
This is how you write the equation of sound wave in terms of the pressure, difference in pressure. Remember, it's not the pressure, it is difference in pressure. Do we understand this? Delta P is not the pressure at any point, it is the difference of pressure between pressure at that point and atmospheric pressure. We understand this?
Yes, sir.
Pakka na, sir?
Yes, sir.
Then, sir, a question comes for you, sir. So apart from this, everything remains same. You must know what we have already done. The equation of the wave remains same. The terms remain same. And we welcome an equation. No, we welcome a question. Come question, come question, come. This is the question that has come on your request. Question number 1. Find the following for the given wave equation. Frequency, wavelength, speed of the sound wave. If the equilibrium pressure of the air is 10 raised to the power 5 Pascal, this is atmospheric pressure. Find the maximum and the minimum pressure. Maximum pressure is the pressure at compression. Minimum pressure is the pressure at rarefaction. Do we understand this? Yes or no?
Yes, sir.
You have 2 minutes to show your talents. Else I will be compelled to do it on my own. So how do we solve this question? This is the easiest question in the entire universe, and we must do it in that way. So, first answers first. How do you get the frequency?
Omega by 2 pi.
Omega by 2 pi. Omega is 3000.
3,000.
3000 divided by 2 pi. That is your first answer. How do you get wavelength? Lambda.
2 pi by k, sir.
2 pi by k. So 2 pi divided by 9. How do you get the velocity v?
Omega by k, sir.
Omega by t. 3000 by 9. If the equilibrium pressure is 1, what is the maximum and minimum pressure? The answer is right in front of your eyes. The answer is right in front of your eyes. The answer is right in front of your eyes. The answer is right in front of your eyes. The answer is right in front of your eyes. The answer is right in front of your eyes. And that is the maximum pressure. Right in front of your eyes, the answer was there, and you were wandering in the universe looking for the next planet to inhabit. But you did not see the closest planet, moon. You can inhabit that. Don't have to go to other stars. Is it so difficult to see this? Right in front of your eyes, the answer was. Anyways, remember this delta P, this wave equation, P, this wave equation is for difference in pressure between the atmosphere and the pressure at any point. So you add it or you subtract it. You add the maximum pressure difference, you will get the maximum pressure. You subtract the maximum pressure difference, you will get the minimum pressure. That's it. Do we understand this? Yes or no? No or yes?
Yes, sir.
See, it was so simple. Anyways, let us move ahead and let us talk about the frequency. Just since we are talking about sound wave, this is what you must understand. What is the frequency of a sound wave? Is the frequency at which my vocal cords are vibrating. It is the same frequency as with the guitar string might vibrate. That is known as the frequency. It's the distance between two consecutive compression or two consecutive rarefaction. If I'm producing sound of a single frequency, then it is known as pure tone. Pure tone. These are the terms that we use. These are the terms that we use in sound pure tone. Do we understand this? Yes or no? This is just for your academic interest. You don't have to write it down. It is just for you to understand that something like this exists. Do we understand this?
Yes, sir.
Audible range for human beings is from 20 to 20 kilohertz. Below 20 hertz, we cannot hear anything. Above 20 kilohertz, we also do not hear anything. Do we know this? Yes or no? No or yes?
Yes, sir.
Yes, sir, you know this. I did not know it. Just now I realize it. Below 20 hertz is known as infrasonic. Sonic is what we hear. Don't have to write this down. You just mark it an important point and just ultrasonic. Ultrasound you might have heard. Ultrasonic above 20 kilohertz. Even we can't hear that. So that is what it is all about. Everyone is understanding this, yes or no? Huh?
Sir.
Hmm. Now, sometimes When we are talking about sound, we always hear this word pitch. Now, this pitch actually relates to the frequency of sound. Your pitch is too loud. Please lower your pitch. A high pitch note of high frequency is called as high pitched. A low frequency note is known as low pitched. Do we understand this? Yes or no? No, yes. This is just for your academic interest. Nothing else, nothing more, nothing less. Do we understand this?
Yes, sir.
Yes, sir or no, sir?
Yes, sir.
That takes us to the next step, my dear friends. And what is the next step? Pressure wave and displacement wave. Now we are going to relate what? Relate the pressure wave with the displacement wave. How do we relate this pressure wave with the displacement wave? And I'm not going to get into that how we derive this result. We are only concerned with the result. Now, if I write the wave equation for this displacement wave, now since wave is also going to travel in the x-axis, the displacement of the particle is also going to be in the x-axis. So I should not use x here. So let me use some other thing. Let me use s for displacement. S is equal to s naught or s maximum sine omega t minus kx. Do you understand what is the meaning of the different terms here? S is the displacement of the particle from the mean position. S naught is the amplitude. Do you understand this? Yes or no? No, yes.
Yes, sir.
And again, this is the wave which is traveling in the positive direction of x-axis. Anyone understands this?
Yes, sir.
Okay. Now, when I write the pressure wave for the same, the pressure wave delta P is equal to delta P naught for the same condition. The pressure wave looks like this. The pressure wave looks like this, and you should remember this. Now, what do you see? The first prominent thing that you see is what? The first thing that strikes you instantly. What is that first thing that strikes you instantly? Huh? But nothing.
Phase difference is pi, sir. Pi by 2.
Open your eyes. You have a beautiful eyes. Open your eyes and see the beautiful universe. Yes. Pi by
2.
2. Yes. Pi by 2. That is correct. Pi by 2. So this pressure wave is ahead of the displacement wave by a phase angle of pi by 2. Do we understand this? So that is the first thing that you should note. Pressure wave is ahead of displacement wave by a phase angle of pi by 2. What it means? What it means? When the displacement is maximum, huh? That means when the displacement is maximum, then
Pressure is minimum.
the pressure is minimum. So when the particle is when the particle is on the mean position, the pressure is maximum. When the particle is on the extreme position, the pressure is minimum. Do we understand this?
Yes.
So that means when S is maximum, that will imply the difference in pressure is minimum. Remember, difference in pressure we are talking about. Everyone understand this? Yes or no? Or this is gone above or saying bye bye. I'm going.
Yes, sir.
Okay, we understand this. Now, there is a relation between these two gentlemen also. And we will not go into deriving it because that is just a wasted exercise. There's a relation between these two gentlemen as well. What is the relation? First, write it. First, understand, then I'll give you time to write. There's a relation between these two gentlemen as well, and you must remember these two relation, the relation between these two gentlemen. This delta P naught is equal to B K S naught. BKS. What is B? What is K? What is S? S naught is obviously your amplitude of displacement, your amplitude of the particle. Particle oscillating ding 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 ding. What is K? Huh?
Wave
But
proportionality constant.
K, that angular wave number 2 pi by lambda. We remember this? 2 pi by lambda. Huh?
Yes, sir.
What is B? B is the only thing that comes here. B, 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 B. B is the bulk modulus of the medium. B is the bulk modulus of the medium. So I'll give you now 2 minutes. Note this down, Aram say. Take a deep breath and read the equations carefully, because if you understand the relation between pressure and displacement, that is the most important aspect of this chapter. I'll give you 2 minutes. Once you have understood the relation between the two waves, we can tackle some problems, and this is the problem that I have for you, and it comes on your screens now. It comes on your screen now. A sound wave of wavelength something something 40 centimeters travels in air. If the difference between the maximum and minimum pressure at a given point is, find the amplitude of vibration of the particles. The bulk modulus is this much. And you have 2 minutes to give me the answer for this one. Let me do it. How are you supposed to do it? The wavelength is given. Well done. The difference between the maximum and minimum pressure is given. So from here I can find out the value of what? I can find out the value of delta P naught. What is the value of delta P naught? Between the maximum and minimum pressure, the difference between the maximum and the minimum pressure, the difference between the maximum and the minimum pressure is given as 2 into 10 raised to the power minus 3. So what will be delta P naught? Between compression and rarefaction, they have given you the difference. So This difference divided by 2 will be your delta P naught. Yes or no? So your delta P naught, the maximum pressure difference becomes 10 raised to the power of minus 3. We understand this, yes or no? Huh? Do we understand this, yes or no? If I draw the pressure wave like this, just for the example, this is the compression, maximum pressure, let us say. This is the rarefaction, minimum pressure, that, let us say, they have given you this difference. Do we understand this?
Yes, sir.
So the delta P naught, the amplitude of pressure difference, becomes 10 raised to the power minus 3. Now I just need to apply that formula. What was that formula? Delta P naught is B K S naught. And I get my answer. Your S naught will become delta P by B into K. K is not given, but lambda is given. So B into 2 pi multiplied by lambda. If you put them correctly with the correct values, the answer that I have is 100 by 7 pi Armstrong units. 10 raised to the power minus 10. Now, can you tell me what mistake you were making? Huh?
Pressure difference, sir.
What difference, beta?
Pressure difference I have taken as 2 into
I
10 to the
know,
power of minus
I
3.
know, I know, I know. I know you will do that, and that is why that is why the question was given. That is why this question was given. Okay, so that was the reason of giving you this question, because I knew that you are going to make that mistake. Anyways, having said that, we have to move ahead in life. Yes or no? No, yes. Now, we are not going to go much into that wave equation, because we have already seen all forms of this wave equation: omega t minus kx, kx minus omega t, kx plus omega t, and all those 2 pi by lambda forms. So that still remains there, right? The only new thing was pressure wave, and we have seen that. Yes or no? No, yes. Huh?
Yes, sir.
So now we will have to move ahead and what? Move on to the speed of sound waves. Remember what was the speed of transverse wave in a string? Can anyone remind me that? Speed of transverse wave in a string? Huh? Speed of transverse wave in a string? Anyone remembers it? We have forgotten? No one remembers it? Huh? Okay, I think your camera, I think your speaker is not working. We remember it. Anyways, now we move on to speed of sound waves. Speed of sound wave. Now, depending on the medium, we will have different formulae for speed of sound waves. Now, To understand this, the basic formula comes from Newton here also. So Newton's formula for speed of sound wave, Newton's formula for speed of sound wave in any medium is root over E by rho. This is valid for each and every medium. What is E here? E here is the coefficient of elasticity. E here is the coefficient of elasticity. Young's modulus, bulk modulus, all those things that are known as coefficient of elasticity. And rho, what is rho? Rho. This rho is the density of the medium. So this formula of Newton is valid everywhere for all the mediums. Do we understand this? Yes or no?
Yes, sir.
Okay. Now we can apply this formula for solid. Now we can apply this formula for solid. So velocity of sound in solid medium becomes y divided by rho. What is this y?
Young's modulus.
Y is the Young's modulus. That is correct. Then for liquids, let me write it here only so that everything comes in one. First, understand this, then I'll give you time to write it. For liquid, it will be equal to root over B by rho. B? What is B?
Modulus. Bulk modulus.
B is bulk modulus. Now, what is the formula for gases? Now remember, this modulus of elasticity for gases depends on different process. If the process is isothermal, then this bulk modulus for gas for that process will be different. If that process is taken as adiabatic, that formula for bulk modulus becomes different. So for gases, if that process is taken as isothermal, which was what Newton did, so for gases, the formula that Newton gave was this: V is equal to root over P by rho, because he has taken the process as isothermal. He assumed that the process of propagation of sound in gas would be isothermal, and therefore he got the bulk modulus as P. The bulk modulus for that process comes out to be P, and that was the Newton's formula. But when we put the value of P, atmospheric pressure, and the density of air, the speed of sound does not come correct. That means there is a problem with this formula. The speed of sound is actually 332 meter per second, but from this formula the speed of sound does not come correct. That means this formula is wrong. It does not mean that it is not bulk modulus divided by rho. It is bulk modulus divided by rho, but that bulk modulus should not be calculated for isothermal process. Then came the next gentleman. Who was the next gentleman? Laplace. And he corrected this formula. So it is known as Laplace's correction or Laplace's formula for the speed of sound, and he gave this formula. Then V is equal to under root of gamma P by rho. Do you know what is this gamma? This gamma, do you know what is this gamma?
No, sir.
This gamma is known as the coefficient of molaris. You can call this as, right now you can call it as adiabatic constant. Gamma is the adiabatic constant. Gamma P by rho. Gamma is the adiabatic constant, you can call it now. He took the process as adiabatic. You have never heard this term gamma? He took the process as adiabatic. Have you ever heard about adiabatic process?
Yes, sir.
In adiabatic process, we have PV raised to the power gamma. Yes or no? Adiabatic process. Do you remember adiabatic process? PV raised to the power gamma.
No, sir.
Not heard about adiabatic process? PV raised to the power gamma. Yes or no? No idea? Gamma is Cp by Cv. Ever heard about Cp and Cv? Okay, note it down, please. Gamma is Cp by Cv. Ratio of specific heat, you can call it adiabatic constant or whatever. Give you 2 minutes to note this down. Once you are done, please let me know. So now we can move ahead, and since we know the three formulae, most of the cases whenever a question on sound waves is going to come, it will be a question on sound waves traveling in gas rather than anything else. So that is the main point of concern, because sound travels in air and gases, and that is where most of the questions to come from. So velocity of sound in gases. Now the formula for this velocity of sound in gases becomes root over gamma p by rho, right? So you can write now it in different ways. Gamma p, and density is mass divided by volume, so you can write the total mass divided by total volume. The mass of the gas divided by the volume of the gas. Now you must know that P into V is nRT. So you can write it as gamma nRT, number of moles, I hope you understand this, divided by the mass of the gas. Number of moles and mass of the gas divided by number of moles will give you the molecular mass of the gas. So you can write it as gamma RT by m naught, where m naught is the molecular mass of the gas. Do we understand this?
Yes, sir.
M naught is the molecular mass of the gas. And this m is the total mass of the gas. So now we have all these legendary formulae all these legendary formulae for velocity of sound in a gas. You must also recollect that the RMS velocity. Have you heard about RMS speed or RMS velocity?
Yes, sir.
The RMS speed or RMS velocity is 3 times RT by m naught. Yes or no? So from here you can get this velocity of sound divided by the RMS velocity of gas molecules. If you find out this ratio, it will be equal to gamma divided by 3. A very, very important result that you must recollect. A very, very important result that you must recollect. Have you noted this down, everyone?
Yes, sir.
Okay. Now we can see the effect of various things on the speed of sound. Number A, effect effect of temperature. Effect of temperature. What is the effect of temperature on the speed of sound in any gas or any medium or in atmosphere? Speed of sound in any medium is directly proportional to root of T. Yes or no? Remember, this T is absolute temperature. Temperature on the absolute scale. Do we understand this? Yes or no? No, yes.
Yes. Yes, sir.
So this speed of sound is directly proportional to temperature, or you can write V2 by V1 will be equal to under root of T2 by T1. Remember, both the temperatures have to be in the absolute unit. You can write it like this, under root of T plus 273 divided by 273. If you take the first temperature as 273 degree 273 Kelvin or 0 degrees Celsius. Let me not write it here. So, do you understand this one? That will confuse you. V2 by V1 will be equal to under root of T2 by T1. Yes or no?
Yes, sir.
Now, we can from here we can devise a formula for speed of sound at any temperature T. Speed of sound at any temperature T will be equal to V naught into 1 plus T by 273 raised to the power of half. This formula is derived from the upper one. That is the one I was going to do, but I have just done it in a different point. What does VT stand for? Speed of sound at temperature T degrees Celsius. What does V naught stand for? Speed of sound at 0 degrees Celsius. Do we understand this? Do we understand this?
Yes, sir.
So this is the formula that you can make. For air, the formula can be further simplified. For air, if I only talk about air, for air, the formula looks like this. V at temperature T will be V naught, and V naught is 332. 332 plus 0.61 times of T. This formula becomes effective for speed of sound in air. Do we understand this, or this has gone above our head saying bye bye sir, I am going sir, bye bye sir, I am going sir?
We understood, sir.
Okay. Shall we move to the next point? Have you noted this down?
Yes, sir.
The second thing would be the effect of pressure. What is the effect of pressure on the speed of sound? We know V is under root of gamma P by rho, which can be written as gamma RT by M naught. So what do you think is the effect of pressure on the speed of sound? If you increase the pressure, will that speed of sound increase or decrease? Yes. What is the effect of pressure? Huh?
Increases.
With increase in pressure, the speed of sound increases. Yes or no?
Yes, sir.
So V, speed of sound, is directly proportional to root of pressure. Yes or no?
Yes, sir.
That pressure has to be in SI unit. Yes or no? That is yes or no?
Yes, sir.
That is absolutely wrong, sir. Speed of sound does not depend on pressure. Speed of sound does not depend on pressure. How is that possible? As long as temperature remains constant. If you are changing the pressure and that causes a change in temperature, that is a different thing. In that case, the speed of sound changes. Speed of sound has not changed because you have changed the pressure. Speed of sound changes because you have changed the temperature. Now, why is that so? Now, if you look at the terms in the blue, the terms in the pink, gamma is adiabatic constant. It is a constant. R, universal gas constant. It is also a constant. M naught, the molecular mass of gas or molecular mass of molecules in air. All these three things are constant. The only variable in that blue thing, in that pink thing, the only variable is T. Yes or no? T is
Yes,
the
sir.
only thing that can change. Rest all are constant. Therefore, I said that speed of sound is directly proportional to temperature. But if you look at this blue equation, in this blue equation, gamma is there, which is a constant, but only that is constant. There are two unknowns or two variables here which can change. The pressure can change and volume can change. In fact, speed of sound will only change when P by rho changes. Do you understand this? When P by rho, that quantity changes, then only the speed of sound can change. When P by rho changes, it effectively means that the temperature changes. Do we understand this?
Yes, sir.
And therefore we say that therefore we say that what? Therefore we say that speed of sound does not depend on pressure. Do we understand this? Because pressure may change, but it may change in such a way that P by rho remaining constant. That means temperature remaining constant, and therefore only thing that can change the speed of sound is temperature and not pressure. Do we understand this? Yes or no?
Yes, sir.
Have you noted this down? Huh? Have you noted it down, bacha?
1 minute, sir.
Okay, let me know once you are done. So we have done this. Everyone understands this? There is no effect of pressure on the speed of sound. Speed of
Yes.
sound does not depend on pressure. You will have to remember all these terms because all these points are going to come as questions in your examination hall. The third point is effect of humidity. Effect of humidity. Remember these points? Effect of humidity. What is the effect of humidity? Humidity of air. Sometimes air becomes very humid, especially in summer seasons. It becomes very humid. What is the effect of humidity? Yes, anyone? Now, when humidity increases, the density of the air actually goes down. Yes or no? Do we understand what I'm saying?
Yes, sir.
When humidity increases, the density of air goes down, and therefore the speed of sound increases when humidity increases. So you must remember this. When humidity increases, density of air decreases, and therefore the speed of sound increases. That is why sound travel faster in humid air. Rainy season, sound moves fast. So if it is raining, the sound will move fast. Do we understand this, or this has gone above? What I think, bye bye. We understand this?
Yes.
Okay. I will just give you 2 or 3 more points, and then I will give you time to write it. Just understand these points, then you write them together. That was the effect of humidity. The next point is effect of motion of air. Sometimes wind is blowing. Sometimes winds are blowing. If the wind is blowing in the same direction as sound, speed of sound will increase. If the wind is blowing in the opposite direction of sound, speed of sound will decrease. Do we understand this? So, when the speed of sound and the direction of wind are in the same direction, the speed of sound becomes v plus w. When they are in the opposite direction, it becomes v minus w. Do we understand this? Do we understand this? Yes or no?
Yes.
Okay. One more point and I'll give you time to note this down. The next point is, and you must remember all these points because any question can come from this. The next point is effect of frequency. Does frequency have any effect on the speed of sound? You must understand that frequency has no effect on the speed of sound. Frequency has no effect on the speed of sound. So now I will give you 5 minutes, 2 minutes, 3 minutes to note them down. Humidity, motion of air, and effect of frequency. Has everyone understood this? Yes or no?
Yes.
Note it down now. Sometimes we have this notion that since V is equal to F lambda, if I increase the frequency, the speed of the sound increases. No. If I increase the frequency, wavelength decreases. Speed of the sound only depends on the medium. Speed of transverse wave or longitudinal wave only depends on the medium in which they are traveling. It does not depend on the frequency. Do we understand this? Yes or no? No or yes? Do we understand this?
Yes.
Everyone?
Yes.
Now, have you noted this down? Everyone has noted this down or you are still noting it down?
No, sir.
You are noting it down?
Yes.
Okay, I'll give you 2 minutes to note it down. Okay, now you have seen the effect of motion. Now, sometimes the sound may not be in the same direction as wind, or wind may be blowing at an angle. Now, if that happens, then what do you do? So you can write wind at an angle. Now we are going to see this. We are going to see this in the coming classes. If wind is at an angle like this, wind is at an angle like this, wind is moving here along the blue direction. My sound source is here. My listener is here. My sound source is here. Sound is blowing in this direction. Then you understand the concept of relative velocity. The speed of sound will become the speed of sound. Original speed of sound is v. The speed of wind is w. In this case, it will become v plus w cos theta. Do we understand this? Yes or no? No or yes? Do we understand this? You raise your hands and let me know that we understand this, sir. Yes, sir. No, sir. We don't know, sir. Do we understand this, sir?
Yes.
Pakka, sir?
Yes. Sir.
No doubt on this, no, sir? Okay. Now you can, if you want, you can draw this table also where you get everything together. And let me see if I can draw it here. Let me see if I can get it here. I think I can get it here. So this is one table in which I have put all the situations of observer and sound and the different velocity of the medium or velocity of the wind. If wind is blowing in the same direction, it becomes, see, this is in the same direction, so you get it added. This wind is in the opposite direction, therefore you get it subtracted. This wind is blowing in this direction, so effectively there is a component here like this, therefore you have the answer like this. Here, the sound is moving like this, wind is in this direction, and therefore you have Vs minus Vm or Vw cos theta. Do we understand I'm trying to explain here? Yes or no? No, yes.
Yes, sir.
We are going to use this in the chapter on Doppler effect, which I think is going to come very soon, maybe in the next class or in the next to next class. Here I will wind off this class here. In this class, we have seen what are the effects of different components on the speed of sound. And tomorrow, I would request you to read what we have done and be prepared. And also, I have told you about this term gamma. You will go back and read your books and find out more about gamma. What is the value of gamma for monatomic gases? What is the value of gamma for diatomic gases? What is the value of gamma for polyatomic gases? Can you do that for me?
Yes, sir.
So you go and find out only mono or diatomic gases. If you can do that, it is more than enough for solving problems right now here. Otherwise, we are obviously going to see this gamma in the chapter on thermodynamics. We'll see it there. Right now, just to solve problems, just see what is gamma for diatomic gas. You understand diatomic gas? O2, H2, N2, all these are diatomic gas. Do we understand this?
Yes, sir.
So you just go and see what is gamma for diatomic gas and what is gamma for monatomic gas, helium, neon, argon, and so on. We'll see. We'll solve questions in the next class, but if you don't remember anything from this class, the next class you will be whitewashed, as South Africa is getting whitewashed in Australia. So please, before coming to the class tomorrow, do all these things so that we can move faster. We get this, everyone?
Yes, sir.
Okay, then I'll see you in the next class tomorrow. Take care. God bless you all. Bye bye.